Good morning, good afternoon everyone, and welcome to episode 5 of this series on how to make a Web3D infinite runner game. In today's tutorial, we're gonna spawn objects in our level, have them move consistently with the grid, and make new ones respawn forever in front of us. Are you ready? Then let's dive in. In the previous episode, we saw how to make the infinite animated grid. We used a little trick relying on shaders to make it much more efficient to compute, thanks to the power of parallel computation of GPUs. And so, overall, for now, not a single object in our scene is actually moving. We are only simulating movement via animation and relative viewpoints. But today we're gonna see how to create and move objects on the grid to populate our level and keep a consistent feel of this infinite movement. So we're gonna spawn two types of objects, the obstacles and the bonuses. The obstacles will be some wide cubes that can be a bit stretched on all three axes and that are placed at random on the grid in front of us. The bonuses will also be placed randomly, but this will be displayed as spheres with various colors and sizes depending on how much score points they give you if you grab them. So to begin with, let's see how to instantiate those objects in our level. To make it easier to move those objects later on, we will reuse the notion of 3D groups that we saw a couple of tutorials ago when we worked on our ship. And so instead of adding the obstacles and the bonuses directly into the scene at the root of the hierarchy, we're gonna create a specific parent for all the objects, both obstacles and bonuses, to define a sub-hierarchy. Let's start by doing that in our initialize scene method before finishing our setup. So I'll just create a new this.objectsParent variable that is a 3.group. Once again, I'm making an instance variable so that it's easily accessible from any other function from the game class. And now we need to create two util methods in our game class, the spawn obstacle and spawn bonus functions. We'll first look at the obstacles because they're a little bit simpler. And the idea here is that we're gonna create a basic cube geometry and then we'll get some random floats for the scale along the three axes. But because all of the obstacles share the same base geometry, this cube, and the same material, we can improve memory management by storing and reusing the same geometry and material variables. Though because those variables don't depend on the instance of our game class, but that they depend on the game itself, we'll make those class variables instead of instance variables. To do this, we simply have to declare the variables in the body of the class, so outside of any function. And I usually prefer to put all my class variables at the top of the class before the constructor. So here I'll have obstacle prefab that defines a new box buffer geometry, and obstacle material that is just a basic material with a light gray color. Now I can use those variables in my spawn obstacle method with the this keyword as usual. So I'll say that I have a new object variable that is a new 3.mesh. And that uses this.obstacle prefab and this.obstacle material. We can actually see how it looks right now. We'll simply add this object to our brand new parent group, so the this.obstacles parent. And in our initialize scene method, we'll add a little for loop that creates 10 obstacles in the level. Now, if I save this, you see that it looks like I have one cube in the middle of the screen at the same position as my ship. And that's because for now, we aren't scaling or positioning the cubes at random, so the 10 obstacles are overlapping each other at the origin point. So let's go back to our spawn obstacle logic and add some randomness. To anticipate some future code, we'll separate the part of the logic that sets these random attributes on the object in a setup obstacle function, and we'll call it in our spawn obstacle method right now, passing in our new object. Okay, we want to get random floats for both the scale along the three axes and a part of the position vector. So first we should actually write up a little tool function to get a random float within a range like this. If you're curious, you can find more info for this on the net, but basically this maps the range of math.random, which is a float between 0 and 1, to the range that you pass in through the min and max parameters. Now let's actually use this to create our scale and position vectors. We'll use 3.js set syntax to update the size and location of our newly created object. So we'll have opt.scale.set, and then I'll just fill in some variables that I found beforehand and that I think look nice for my game. But of course, depending on your game and your design, you may have to tweak those. And for the position, it's a bit more complex because we don't want it to be completely random. What we want is the following. For the x position, it should be related to our current x position, so the x position of the ship, because we want the objects to spawn somewhat in front of us. Even if we press the arrow keys and we derived away from the initial x equals 0 position, we want the objects to be in front of us, and so we will consider a reference x position, and then we'll add a random offset to it. For the y position, it depends on the size of the cube, because we don't want it to be centered on the grid, but to be placed on it. So the bottom of the mesh should be at y equals 0, meaning that we have to translate the entire mesh itself by half its height along the y-axis. And finally, for the z position, it's a bit more problematic, because we have to create the objects in front of us at the horizon, so it is related to the current position of the ship, but this time it's along the z-axis, and remember that we are not actually moving along the z-axis, so our z position isn't actually changing. This means that we need to find a way of keeping track of our current travel distance, so of our current offset, even though we haven't actually moved. We will see a bit later on how to get that. For now, we'll just assume that we know this reference z position. And so if you suppose that you have this position, what you want to do next is take the half size of our grid. So in our case, it's 200 units over 2, so that's 100 units. And you want to move further away than this distance to create new objects far enough from our current viewpoint. So all of this zone is allowed for spawning our objects. And we'll just say that we start from this reference z position, then we add the half grid size offset, and then we add a random offset that is somewhere between 0 and 100 to populate this soon to come piece of the level. The reference positions will be passed in as ref xpos and ref zpos. That will be input parameters, and they will both default to 0. But remember that we will see very soon how to get the updated values. Okay, so if you save your file again, you'll see that there are now 10 cubes in the distance. This is really cool. But before we make the objects move and come towards us, let's actually take care of the bonuses first. The overall idea is pretty much the same as for the obstacles, except that some of the values for the bonus size and its color depend on the price of the bonus, so how much score points it gives you if you grab it. We will reuse the same technique as before and have a bonus prefab class variable to reuse the same geometry. This time it's a sphere. But for bonuses, we can't actually share the material because all bonuses will have different colors, so they will each have their own material instance. Okay, so now we can go back to our spawn bonus function and create a new object that will be a 3.mesh, and that uses the bonus prefab and a new mesh basic material. We don't really care about the color here because we will be reassigning it very soon, depending on the price of the bonus. So just like before, I'll separate the logic that assigns the random attributes in a setup bonus method and call it here. Now, the price of a bonus is picked at random between 5 and 20 score points, with an additional method that is called randomInt because we only want integers. And so this method is quite similar to the random float, except we claim the values to only get integers. And And with this function, we can now go to our setup bonus function and say that the price is just a random int between 5 and 20. We'll also compute the ratio of this value compared to the maximum possible price, so that's 20, and the ratio is just price divided by 20. And now we can use both those values to deduce the size and the color of the bonus mesh. The size is simply half the ratio. It will be the same for the 3 axes because we want a sphere, so we just said that size is ratio times 0.5 and that we scale the object using size for the 3 components. For the color, it's a little bit more tricky. What we want is to have something that goes from blue for low prices to red for high prices. We could write these blue and red limits in the hexadecimal color format, which is quite usual for web development, but this would mean we have to add some tiresome math computation in the middle to interpolate for the intermediary price values. So instead, to get this linear gradient between blue and red easily, we will use another well-known color format, that is the HSL format, that stands for hue saturation lightness. With the HSL format, colors are organized on a disk. We usually say that the 0 degree angle is on the red, on the right, and we can then increase this angle to change the tint of the color. So we get blues for angles around 180 to 240 degrees, and we're back to reds around 360 degrees because we've come full circle. On the other hand, the distance to the center gives you the saturation of your color. So if you stay at the same angle and move along this line, the tint doesn't change, but the closer you are to the center, the whiter the color. We say that it has low saturation, and the maximum saturation is on the edge of the disk, where you have your full tint. And finally, lightness is often represented on a third axis, actually turning the disk into a cylinder. So that's the HSL cylinder. And the lightness simply tells you how light or dark the color is. So if you stay at the same point on the disk and only move vertically across the cylinder depth, you'll get variations of your color with lighter or darker tones. And the central axis of the cylinder is where you have the neutral or achromatic colors. It's only grays, ranging from full black at the bottom to full white at the top. Now, in our case, we actually don't need to move much on the HSL cylinder. We only care about the tint of a color, so that's the angle on the disk. And what is great with the HSL format is that it makes it really easy to get equivalent colors where only the tint changes. Just keep the same saturation and lightness levels and then change the hue to get various tints. So here we want to get blues for low prices and red for high prices. So we will simply remap the bottom half of the circle. So that's an angle range between 180 and 360 degrees. We want to remap this to our 5 to 20 price range. But since 3.js renormalizes the hue value, we actually want to remap the 0.51 range. And this can be done very easily with the following formula. So const hue is just 0.5 plus 0.5 times ratio. And now we can simply use 3.js setHSL function to update the color of the material on our new object. We just need to put full saturation and a medium lightness to get well-contrasted colors. And now the final step is to just place our bonus object in the scene. It's the exact same thing as for the obstacles, so let's just copy back those few lines and re-add our ref xpos and ref zpos input parameters. And in the end, we just have to make the new object a child of our this.objectsParent group. And now we can go back to our initialize scene method and do another for loop for the bonuses. So we'll also spawn 10 objects using the spawn bonus function. And if you save your file, you'll see that there's now some colored bubbles in the distance. So okay, we've successfully created our objects. the obstacles and the bonuses. Now we want to make them move and come towards us so that it matches the grid animation and we still feel like it's moving forward. To do this, we'll take advantage of the fact that all of our objects are stored in the object's parent group. This means that moving this group will automatically move all of the objects inside it. So basically, we can just go to the update grid method and add a little line below the one that updates the shader of our grid. And we'll just say that this.objectsParent.position.z equals this.speedz times this time. I'll also move the speed z variable to be defined in the constructor rather than the createGrid method, because I think it's better to centralize all of our variable initialization logic in one place. So now if I save this, you see that the objects are slowly coming to me. And I can just increase the speed value a bit to make everything move faster, both the grid and the objects. And yeah, so far so good. We have spawned and moved our objects. But of course, now we don't really have an infinite level anymore, because as soon as the objects have been dragged too far and that they are behind us, we can't see them anymore. So since we aren't creating new ones, we just lost all of our objects and we don't have a game to play anymore. Okay, now, should we just keep on creating more and more objects to fill this empty space in front of us? Well, in fact, the better solution is to use a common game dev pattern that is object pooling. Something that is very important whenever you do some game dev or even programming in general is that creating and destroying objects is costly. That's because continuously recreating and deleting stuff means that you're doing a lot of memory allocations, deallocations, and reallocations, which is always inefficient. This is mostly due to caching and the way that computers sort objects in memory. They always prefer to have objects in neatly consecutive chunks of memory, but destroying an object means that you're deleting a chunk, which leaves a hole. And this is the problem called memory fragmentation. When you have that, it's really bad for memory because you either have to account for this empty space from that point on, or move everything that is further down this memory line to remove the hole, neither of which is quick or free to do. So it's usually way more optimized to keep the same objects as much as possible and simply move them around in your scene to fake the apparition of new ones. This way, you don't create holes in your memory lines. Once an object has reserved a spot, it keeps it until the end of the process, and it doesn't collide with the rest of the objects in memory. So the object pooling pattern relies on defining some of your objects as obsolete and resetting them from time to time, but never recreating new ones or destroying them completely. When using this pattern, we just simulate their appearance or disappearance via various tricks, but the memory manager is happy because we ask for one big chunk of continuous memory at the very beginning, and then that's it. You keep working with the same objects in memory over and over again. Note that you can have an object pool that is larger than the number of objects that are shown initially. Your routine may reveal some only after a while, but the whole point of that pattern is that the pool should have as many spots as the maximal number of objects needed in your scene at the same time. Here we'll just stick with the 10 obstacles and 10 bonuses, so that's 20 objects in total. We create those at the very beginning in our initialize scene method, and then we just have to find a little bit of logic that resets them so they look like brand new objects when they are obsolete. Okay, now what does it mean for us that an object is obsolete? Well, it's simply that it's gotten out of sight, that it is somewhere behind us. Since the ship is not really moving and it's stuck at z equals 0, an object is basically obsolete if its position in the world along the z-axis is over 0, so if it's more than 0. And in that case, we simply need to recompute its scale and position, that's for an obstacle, or its price and position, that's for a bonus, and it will feel like we just created a brand new object on the terrain, somewhere in front of us. So we'll handle all of this in our updateGrid method. And the first thing we have to do is go through all of the objects in our scene, so the obstacles and the bonuses. And because they are children of our objects parent group, we can actually use the 3.js traverse method that allows you to iterate through a sub-hierarchy in your scene and run some logic for an object and all of its children. So here I'll just traverse the this.objectsParent object, and the first thing we want to do is check that we're on a child and not the group itself. So let's just add a little if check on the type of the child variable. It's just if child instance of 3.mesh, because the parent object is a group, so it won't run this routine. And now that we know we're on an obstacle or bonus object, we can just check if its Z position is more than 0. We just need to be careful though to take its world position, or in other words, the position it has inside of its parent relative space. So that's the object's parent group relative space, and add it the position of the parent, because the overall offset is given by the parent. So summing the two will give us the actual world position. And so now in here, we'll want to reset the object using either the obstacle or the bonus initialization routine. The thing is that for now, we can't actually distinguish between the two. So we don't know which part of the logic to call. We don't know if we should be setting up an obstacle or a bonus. To fix this, we can add some custom user data on our objects to make it easier to differentiate between the two types. This is a bit like the buffer attributes we saw in the previous episode when we created our grid, except it's not at the geometry level, it's at the mesh level. So 3.js has this specific property on meshes, the .userData property, where you can store whatever you like, and it will just be passed around with the object all throughout its lifetime. So let's set this property to a little JavaScript object with just one key, the type, and that's a string that says obstacle for the obstacles and bonus for the bonuses. Now, going back in our updateGrid function, we can access this and know if we're working on an obstacle or bonus, and so we'll be able to call either the setupObstacle or setupBonus function. The first parameter we pass is the object to apply the modifications on, so in our case that's the child variable. But then remember we have to get the reference positions along the X and Z axis to properly shift the spawning points of the objects. This will make sure that the objects and the bonuses always appear somewhat in front of us. So the reference X position is easy to get, it's simply the ship position on this axis, because we'll see next time that we will get the user inputs with the arrow keys and we'll actually convert them to translations along the X-axis. So the ship position will indeed change on this axis. On the Z-axis, however, we are not moving, so the ship position is always 0. What is moving is the object's parent group. This one, we are continuously sliding it backwards. So to get the current position along the Z-axis, we can simply take the opposite of the position of this object. Something you can do if you want to showcase your JavaScript skills is to actually define those parameters beforehand in an array, because you see that they are the same for the two functions. So to factorize my code, I will just regroup them into a params variable. And then I'll just pass this array to my functions as input parameters using the spread operator. And so now if I save this, you see that we have reproduced this feeling we had before of gliding along the grid. And now we have objects on this grid, there are obstacles and there are bonuses, and there are infinitely many. Basically, every time an object gets behind us, another pops far at the horizon to replace it, except it's the exact same object, we just moved it. So okay, that's really cool. Today, we've seen how to spawn both obstacles and bonuses in our level, how to move them consistently with the grid by reusing 3D groups, and finally, we saw how to do object pooling to pre-instantiate all the objects that are needed at the beginning of the game, rather than just creating and destroying new ones over and over again, which avoids running into memory fragmentation issues. Next time, we will see how to get the arrow key inputs and handle them in our key down and key up functions to make the ship move along the x-axis and slalom between the newly created objects. So I hope you enjoyed this tutorial, and I'll see you in the next one.